Today, we build the backbone of arithmetic word problems: ratio and proportion. If percentage was the master key, ratio is the master framework, and 8212, the way we compare quantities and share things out fairly. And its reach is enormous. Partnerships where profit is split among investors. Mixtures and alligation, where ingredients are combined. Problems on ages, on speed, on work, and 821, 20912. Almost every arithmetic word problem is underneath a ratio problem in disguise. The good news is that the core ideas are few and beautifully simple, and once you truly understand them, a huge class of questions that look different on the surface collapses into the same handful of steps. Today, we will learn exactly what a ratio is, how to divide any quantity in a given ratio, what proportion means, and how to solve it in seconds with cross multiplication, and how direct and inverse variation work. Master this, and you gain a framework you will use in almost every quant topic that remains. Let us build the backbone. Here is our path for today. First, what a ratio really is. Second, equivalent ratios and simplifying. Third, dividing a quantity in a given ratio. Fourth, proportion and cross multiplication. Fifth, direct and inverse variation. And sixth, combining ratios and where they feed. Let us begin. Let us start with the true meaning of a ratio, because a clear picture here makes everything downstream easy. A ratio is a way of comparing two quantities of the same kind, showing how many times one contains the other. We write the ratio of a 2b as a colon b. If a class has 10 boys and 20 girls, the ratio of boys to girls is 10 to 20. A ratio does not tell you the actual amounts by itself. It tells you the relative sizes and 80-5, the relationship between them. That distinction, relationship rather than amount, is the heart of the whole topic. Two things matter for a ratio to make sense. First, the quantities must be in the same units before you compare them, and A2 and 4, you cannot form a meaningful ratio of 1 meter to 50 centimeters until you convert them to the same unit, giving 100 to 50. Second, a ratio is usually expressed in its simplest form by dividing both parts by their highest common factor and 8/2 tau, so 10/2 simplifies to 1/2. That HCF you learned 2 classes ago is doing quiet work here. Think of a ratio as the recipe, not the meal. A ratio of 1:2 for boys to girls tells you the pattern, and 80-112, twice as many girls as boys, and 80-112, whether the class has 30 students or 300. The same ratio describes countless different actual sizes, all sharing the same proportion. Holding this idea, and 8-112, that a ratio is a scalable pattern, not a fixed quantity, and 8-112, is exactly what lets us stretch and shrink it to fit any problem. So the takeaway, a ratio compares two quantities of the same kind and shows their relative sizes. Written a colon b, it needs the same units and is written in simplest form using the HCF and A212, and above all, it is a scalable pattern, a recipe rather than a fixed amount. Because a ratio is a pattern rather than a fixed amount, the same ratio can be written in many forms, and A212, and moving fluently between them is a core skill. If you multiply or divide both parts of a ratio by the same number, its value does not change. 1:2 is the same ratio as 2:4, as 5:10, as 50-100, 8:121. They are all equivalent ratios, all expressing the identical relationship Na212, 28:12. This is exactly like equivalent fractions. And in fact, a ratio A to B behaves just like the fraction A over B. Seeing the ratio-fraction connection that you bring all your fraction skills to bear. This scalability is what makes ratios so useful in problems. When a question tells you two quantities are in the ratio 3:5, it is really telling you there are 3 parts and 5 parts of some common unit and 80-102. And the actual amounts are 3 times that unit and 5 times that unit, whatever the unit turns out to be. So you can write the two quantities as 3x and 5x, where x is the size of one part. That little step, and be 85-12, turning a ratio into 3x and 5x and be 85-12, is the single most powerful technique in the entire topic. Simplifying is the reverse move and equally important. Given a messy ratio, like 12 to 18, divide both parts by the HCF6 to reach the clean form 2 to 3. Now, simplest form makes ratios easy to compare and to work with, and it is often the form an answer is expected in. So you should be comfortable traveling both ways along the chain of equivalence and 81 to 1, scaling a simple ratio up to real numbers and reducing a messy one down to its simplest form. So the takeaway, multiplying or dividing both parts by the same number gives an equivalent ratio. Just like equivalent fractions, represent a ratio A to B as a x and bx to bring in real amounts, and simplify messy ratios using the HCF and A to 100 tool, moving both ways along the chain fluently. Here is the most common ratio question of all, and the one technique you must be able to do without thinking: dividing a quantity in a given ratio. Suppose you must divide 1200 rupees between two people in the ratio 2 to 3. The method is beautifully simple. Add the parts of the ratio to get the total number of parts. 2 plus 3 is 5 parts. Then find the value of one part by dividing the total quantity by the total parts. 1200 divided by 5 is 240 per part. Finally, give each person the number of parts. The first gets 2 parts, 480 rupees. The second gets 2 parts, 720 rupees. Notice the elegant structure of this method, because it generalizes to any number of shares. Total parts, then value of one part, then multiply out for each share. Whether you are splitting money among 2 partners or 3, or dividing a distance, or sharing work, the same 3 steps apply. And there is a built-in check. The shares must add back up to the original total and 82 fall. 480 plus 720 is 1200. So we know we are right. Always use that check. It catches errors instantly. This single skill quietly powers a whole family of exam favorites. Partnership problems divide profit in the ratio of investments. Mixture problems combine ingredients in a ratio. Many word problems produce 2 and 80-20 share this quantity in this ratio. And 80-20, 180-21 master the total parts method until it is automatic, and all of these become the same easy calculation wearing different stories. It is one of the highest return techniques in quant. So the takeaway, to divide a quantity in a given ratio, add the parts for the total, divide the quantity by the total to find one part, then multiply for each share and A2 to power, check that the shares sum to the original and A2 to power, and this one method powers partnership, mixture, and countless sharing problems. Now we move from a single ratio to the relationship between 2 ratios, which is called proportion and A200 hull, and it unlocks a fast solving technique. A proportion is simply a statement that 2 ratios are equal. We write it as a is to B, as C is to D, meaning the ratio A to B equals the ratio C to D. For example, 2 is to 3 as 4 is to 6, because both ratios simplify to the same thing. The 4 numbers are called the terms. The 2 outer ones, A and D, are the extremes, and the 2 inner ones, B and C, are the means. When 4 quantities are in proportion, they hold a fixed, balanced relationship. The powerful property of any proportion is this: the product of the extremes equals the product of the means. In A is to B, as C is to D, A times D equals B times C. This is the famous cross multiplication, and it is the engine that solves proportion problems. Whenever 3 of the 4 terms are known and 1 is missing, cross multiply and solve in a single step. If 2 is to 3 as x is to 12, then 2 times 12 equals 3 times x, so x is 8. One line, one answer. This is why proportion is such a workhorse. An enormous number of exam problems are at heart, and A26C on 3 quantities given, find the 4th in the same relationship, and A2 and cross multiplication cracks every one of them instantly. Scaling the recipe, converting units, working out how far you travel in a different time at the same speed, and A212 all are proportions. Once you can spot that a problem is really a proportion, the solving is trivial. The skill is the spotting. So the takeaway, a proportion states that two ratios are equal with extremes and means. And its key property is that the product of the extremes equals the product of the means and A2112 cross multiplication and A2112, which instantly finds any missing fourth term when the other three are known. Proportion comes in two flavors, and telling them apart is essential, because using the wrong one gives an answer that is not just off, but backwards. In direct variation, two quantities increase and decrease together. More of one means more of the other, in the same ratio. Buy more items, and the total cost goes up proportionally. Work more hours at a fixed rate, and you earn more. If you double one, the other doubles. Here the ratio between them stays constant, and you set up the problem as one straightforward proportion and A2112 as the first quantity is to its value, so the second is to its value. In inverse variation, the two quantities move in opposite directions and A2200 fall. As one increases, the other decreases. The classic example is workers and time. Put more workers on a job and it finishes in less time. Or more speed, less time for a fixed distance. Here, crucially, it is not the ratio, but the product of the two quantities that stays constant. So if 6 workers take 10 days, then 12 workers and A2112, double the workers and A2112 take 5 days, because 6 times 10 equals 12 times 5. Double the workers, half the time. The single most important decision is recognizing which type you face. And there is a simple test. Ask whether increasing the first quantity should increase or decrease the second in the real situation. If they rise together, it is direct. If one rising makes the other fall, it is inverse. More petrol, more distance, and A25 direct. More taps filling the tank, less time, and AT or 2 inverse. Get this recognition right, and you set up the calculation correctly. Get it wrong, and you will confidently compute the exact opposite of the answer. So the takeaway, in direct variation, quantities rise and fall together, and their ratio is constant. In inverse variation, one rises as the other falls, and their product is constant, and 8 hoa 200, and the key scale is asking whether, in reality, increasing one should increase or decrease the other. A common exam twist gives you ratios that share a link and asks you to join them into one A212, a skill worth isolating because it looks harder than it is. Suppose you are told the ratio of A to B is 2 to 3 and the ratio of B to C is 4 to 5, and you need the combined ratio of A to B to C. The problem is that B appears as 3 in the first ratio, but as 4 in the second, and K2 fall. The same quantity described by two different numbers. To join the ratios, you must make B in 39, S value the same in both. The technique is to scale each ratio so that the common term matches and the natural common value is the LCM of the two B numbers. Here B is 3 and 4, whose LCM is 12. Scale the first ratio 2 to 3 up by 4 to get 8 to 12. Scale the second 4 to 5 up by 3 to get 12 to 15. Now B is 12 in both. And you can simply read off the combined ratio. A to B to C is 8 to 12 to 15. The H, C, F, and L CM skills from an earlier class are quietly doing the work again. Notice how the topics interlock and 80-60, and this is the deeper lesson of quant. H, C, F, and L, CM feed ratio. Ratio feeds partnership, mixture, and variation, percentage threads through all of them. You are not learning isolated tricks, but a connected toolkit where each tool supports the next. Combining ratios is a small technique, but it perfectly shows how the fundamentals you have built compound into the power to solve richer, multi-step problems. So the takeaway, to combine ratios sharing a common term, scale each so that the common term matches an A212 using the LCM of its two values, an A212, then read off the joint ratio, and notice how HCF, LCM, ratio, and percentage interlock into one connected toolkit. Let us see just how wide this framework reaches. because ratio is genuinely the backbone of the arithmetic section. Several major topics are almost pure ratio. In partnership, profit is divided among partners in the ratio of their investments and 80 to fallible, often weighted by time and 80 to fallible, which is exactly the divide in a ratio skill. In mixtures and alligation, ingredients are combined in ratios, and the price or strength of the mixture is found through ratio reasoning. Problems on ages typically give the ratio of 2 people and 99s ages now and some years ago, solved by the 3x, 5x technique. Each of these is ratio wearing a costume. Ratio also underpins topics you might not expect. Speed, distance, and time are locked together by proportion and 8 high or 12. Direct between distance and time, inverse between speed and time. Time and work problems compare rates as ratios. Even profit and loss and data interpretation lean on ratio thinking to compare quantities. The framework you're building today is not one chapter among many. It is a lens you will look through for much of the rest of quant. This is why we call ratio the backbone. Percentage was the master key, opening individual locks. Ratio is the skeleton that holds the whole body of arithmetic together. When you can look at a partnership, a mixture, an age problem, or a speed question and immediately see the ratio underneath, the surface differences stop mattering, and a large, intimidating section of the syllabus reveals itself as variations on a few simple familiar moves. So the takeaway: ratio is the backbone of arithmetic and 81 tool, directly powering partnership, mixtures, ages, and speed time problems, and threading through work, profit, and data interpretation in 82112. So mastering it lets you see a whole section of the syllabus as variations on a few familiar moves. Let us close by turning this framework into fast, confident exam performance. First, make the 3x technique your reflex. The instant you see a ratio in a problem, write the quantities as multiples of x and 8200, 3x and 5x, or 2x, 3x, and 5x and 8200, and translate the rest of the problem into equations in x. This single move converts almost any ratio word problem into simple algebra you can solve quickly, and it works across partnership, ages, mixtures, and more. Practice it until reaching for x is automatic the moment a ratio appears. Second, dream the two decisions that decide correctness, dividing in a ratio by the total parts method, and distinguishing direct from inverse variation. For the first, always add the parts. Find one part, multiply out, and check the sum. For the second, always ask whether increasing one quantity should raise or lower the other. These two decisions are where marks are won or lost, so make them deliberate and habitual, rather than rushed. Third, remember and exploit how ratio connects to everything else. Keep your H, C, F, and L, CM sharp for simplifying and combining ratios. Keep percentage fluent since it interweaves constantly. And when you meet partnership, mixture, or speed problems later, consciously recognize the ratio skeleton inside them. The student who sees the common framework solves the whole family with one set of skills, while others treat each as a separate mystery. That unified view is exactly what fast, high-scoring candidates possess. So the takeaway: make the 3x technique automatic, be deliberate about the total parts division and the direct versus inverse decision, and consciously exploit how ratio links to H, CF, LCM, percentage, and every arithmetic topic and 80-100 wall. And this backbone will carry you through a large share of the quant section. Let us gather the whole class in one breath. A ratio compares quantities of the same kind and is a scalable pattern, and 821212, a recipe, not a fixed amount, and 821212, written in simplest form. Equivalent ratios come from multiplying or dividing both parts alike. Represent A to B as x and bx to bring in real numbers. To divide a quantity in a ratio, add the parts, find one part, multiply out, and check the sum. A proportion is two equal ratios. The product of the extremes equals the product of the means, and A200 dual. Cross-multiply to find any missing term. Direct variation keeps the ratio constant, In-bus variation keeps the product constant, and AT1-2 how ask which way the quantities really move. Combined ratios by matching the common term through its LCM, and C ratio as the backbone of partnership, mixtures, ages, and speed. Next class and A212 simplification, the fast arithmetic that speeds up everything. One idea at a time. So that is ratio